Hello everyone. Today we'll look at a cool Python project which simulates the Enigma machine from World War II. This video is divided into two main parts. The first part aims to explain what the Enigma machine is and how it works, and the second part is a demo of the Python file that I've programmed. So let's move forward and look at what the Enigma machine is.
An Enigma machine is a famous encryption machine used by the Germans during World War II to transmit coded messages. An Enigma machine allows for billions and billions of ways to encode a message, making it incredibly difficult for other nations to crack German codes during the war. For a time, the code seemed unbreakable, and rightly so. Due to the combinations that are possible due to this machine, it is impossible to brute force your way through it. And techniques like statistical analysis don't apply to this machine either. Therefore, the Germans were very confident about their communications during World War II, but Alan Turing and some famous mathematicians at Bletchley Park successfully broke the Enigma code and saved millions of lives and shortened the war by at least 2 years. So let's take a look at what the Enigma machine is. It's sort of a box here, and this is one of the earlier versions of the Enigma. We can see if a German soldier opens it, there's instructions here in German, there's rotors, there's a lamp board, a keyboard, and a plug board. So what a soldier would do is he has a message to encrypt. Let's say the message is cat. He presses C. Let's say the letter S lights up on the lamp board. He presses A. Let's say the letter W lights up on the lamp board. He presses T. Let's say the letter X lights up this time. Then the message, encrypted message, finally would be SWX. He would have to make note of the initial settings that he used, which positions the rotors were in. Each rotor could take 26 positions initially from A to Z, and there's plugboard settings, and we'll discuss that in a second. He records that, and he has to send these settings to the other end so that they can set their machine to the same initial settings and decrypt the message correctly. Now let's take a look at what the plugboard is. So a plugboard is basically connecting two letters with a conducting wire. They used to have 10 wires, and they would connect 10 letters with a set of another 10 letters. So in total, 20 letters would be connected to each other and 6 would be unconnected. So what happens when something is connected? For example, let's say W is connected to R here. If W is connected to R, anytime you press W, the machine actually takes in R, and vice versa. When you press in R, it takes in W. In this way, it swaps the letters. But if this was the only thing going on in the Enigma machine, it would not be unbreakable. In fact, it would be pretty easy and almost as easy as a conventional Caesar cipher. So what else is the difference? Let's see. There's rotors involved in the process. So let's take an example here just to understand how the Enigma works exactly and its inner workings. Say the letter A was pressed. When the letter A is taken to rotor 1, it encrypts it as E. The E is sent to rotor 2 and gets encrypted as an S. The S is sent to rotor 3 and gets encrypted as a G. Now, it's important to note that we're just taking the example of rotor 1, 2, and 3 here. In reality, the German soldiers had 10 rotors to choose out from in any order they wished, but they basically performed the same task. So our code uses 3 rotors to demonstrate the principle correctly. What happens after rotor 3? Rotor 3 will send in the encrypted letter, which is G, and G gets sent to a reflector. Reflectors are fixed in space and not customizable, unlike the plugboard. We've used reflector B to demonstrate the working of the Enigma in our project. Reflector B converts a G to an L. Now the inverse of these operations happen. So rotor 3 converts the L back to an F, and rotor 2 converts the F back to a W, and finally rotor 1 converts W back to an N. So finally we get the letter N. If the letter N is connected to a plugboard, it's going to be swapped by the letter it's connected to, otherwise it's just going to remain N. Even with all of this, this is a very symmetric algorithm system and it could be broken very easily. So what's the catch here? Why is the Enigma so unbreakable? And the main reason here is that you may have guessed it from the word rotor, that they rotate. After each letter is encrypted, let's just say, for example, that rotor 1 is the fast moving rotor, which just means that it's the rotor to the right. And we'll discuss why it's called the fast moving rotor in a second. The rotor 2 is the medium moving rotor, and the rotor 3 is the slow moving rotor. Then what's going to happen is after A gets encrypted, rotor 1 is going to shift by 1, and now A gets connected to K, B gets connected to M, and so on. When rotor 1 has made a full rotation of 26, then rotor 2 will shift by 1. And similarly, when rotor 2 shifts by 26, rotor 3 will make a turn. In this way, everything is in a state of flux. So if you press A twice, you won't get the same letter back, which is the true beauty of the Enigma machine. Also, of course, it had its own problems like the key distribution problem, and this led to its ultimate downfall. Let's move forward and look at our code now. Here we have all our files for the alpha version, beta version, the GUI, and so on. Feel free to play with the code on my GitHub. The link's visible here. We have a .exe file here. We're going to use that to investigate our GUI, and that's going to open up right here. We can see 3 rotor positions, a text box to enter your message, a text box for the output. If you click help, it will walk you through how to use this simulator. And if you want to learn more about the Enigma machine, it guides you to this link, which is what I used earlier in the video to explain the inner workings of the Enigma. You can click OK and go back to start playing with it. So let's say we choose our initial settings as CAE, or actually CAT, and I want to encrypt the message cats are funny. And I press this, I get an encrypted message. Now, let's say I copy this message and put this back in. Now, notice that the rotors have moved just like they would in an Enigma machine. And with these settings, we'll just get jumbled values, no matter how close to the initial positions we are, even by one letter. Let's say we have CAS instead of CAT, we'll still get something entirely else. But if we go back and put it exactly as CAT and press run, we're going to get our message back. Cats are funny. And this is true for any message of any size. Now, let's try doing something else. You must have noticed this export button. So let's say, for example, we encrypted some messages, but we don't remember what initial settings we used, and we also want a copy of what the encrypted messages came out as. So we can just click export, and we'll have all of those at one place. Let's say we encrypt a new message saying the Russians are coming, and we press run and export. So a file called export is created here, and we get our messages along with our initial position here. So let's say I copy this back and make note of the fact that it's CBH. I can go back, set this to CBH, put in that message, run it, and we get our message back. The Russians are coming. Let's try this with something even more original. This is a letter from the actual World War II written by a person to her fiance. Let's copy this message right here and plug that in. So we have the initial position CCE right now. I press run. We have the message here. I click export. It's going to make a file in the directory called export2 because it's a new message. We take note of the fact that it's CCE here. We copy this message back, press clear, set this to C, C, E. paste it, run, export it, and we have export 3 here, and you can read, "My dearest Will, I feel I must write you again, and dear, although there is not much news to tell you," and so on. You can see the point here. And what the soldiers would do is they would have capital X's, so it would be easier to read. In any case, we can go back, clear this, and now let's see what's happening in the background, really. Let's say in EGC, I'm encrypting the word cat. You can see on the console that the rotors are working, and in the sense that a rotor 2 is encrypting the word C to Z, and then the rotor 1 is encrypting Z to F, and the reflector is converting F to S, and it sends back the letter S to rotor 1, which converts it to O, and so on and so forth till the entire message is done, and we get the message FTU. We also have the plug board. If you're wondering where that went, we've just kept that in the code itself, easily customizable. For example, right now in the state where the code is operating, A is just being swapped with A. It's easier to use from the user, and the GUI is not unnecessarily convoluted. But for example, if I were to put G here, then A would be connected to G. And if I have C here and I put in Z, C will be connected to Z, and they'll be swapped during runtime. You can test this by yourself if you like. In the actual code, we actually have 3 modes: a console mode, an Arduino mode, and a bank encryption mode. Now, the Arduino mode makes use of a rotary dial and a button and an LCD screen to input the messages, choose the rotors, and so on, and lends a practical flavor to it. So, fun fact is, in Germany, before the Enigma was used at war, it was used by banks. And I have a C++ banking program, and this can be used to encrypt all the passwords from the accounts from the banks. We won't go into detail of those right now because time constraints, and since we already have covered a lot of features. I had a lot of fun making this. A huge thanks to Alan Turing and Stack Overflow, and hopefully we'll meet again with another fun project. Thank you.